recording on this computer. All right. So on Wednesday, this is where we stopped. So we were talking about friction. And what is friction? Let me see if I have my notes here. Yeah. So we talked about friction being a force. When we say a force, means it's a vector, means it has a magnitude, it has direction, and it's a force. The magnitude is proportional to the normal force, and the direction of it is opposite the direction of movement or the potential movement. All right. And we talked about this graph here, and that's important for us to understand this graph because different problems have different wordings. Sometimes it says find the biggest force. Sometimes it says find the minimum force. And each of those, they are referring to this force here, but the wording can be a little bit confusing. If you understand this graph here, that we keep going up on the friction force until we reach a point. That if we increase our force P here, even a little bit, the block or whatever we're dealing with starts moving. And that's when we call impending motion. It means it's ready to be moved. It's not moving yet, but it's ready to be moved. And that's where we can use this equation for that exactly that point. All right. So some problems tells you find the minimum force required to move the block. Okay. So I want you to pay attention here a little bit. So some problems tells you find minimum force required to move the block. Okay. Sometimes it says find the maximum force that can be applied before the block is moved. Or before this block starts sliding or slipping or all of that. So see, they are both saying the same thing and they're both referring to this force P. Because after this point, there is movement. So this force is the minimum force that you need to start moving the object. At the same time, this is the maximum force that can be applied before the movement happens. All right. So that's one thing I wanted to mention to avoid confusion. And that's why it's important to understand this graph and what it means and what each side of it meaning. Okay. So before we continue, any questions about friction or anything that we mentioned on Wednesday or anything from my video that you had questions? Okay. So let's get back to this problem. I know it was kind of quick and rushed towards the end, so I'll go over it one more time and make sure everyone is understanding what is happening. So this problem said there's a bar with a uniform weight of 100 pounds and it's just sitting on an edge, kind of like at point A and B. Find the minimum, does it say minimum? Yeah, the smallest coefficient of static friction. And it says assume that both point A and point B have the same coefficient of static friction. Okay, so same material, everything's same condition. So what we did, we drew a free body diagram. That's the first thing we do in all of these equilibrium problems, right? And the 3 steps are still the same 3 steps that we always follow. The first one is outline and isolate whatever that you're drawing the free body diagram of. You're drawing free body diagram of the bar, so we isolate and outline of the bar. Step 2 is put active forces. The active force that I see here, the only thing is the 100 pounds. It's the weight of the bar that is trying to mess up the equilibrium. Step 3 is put reactive forces. Okay, so NA and NB are nothing new for us. It's something that we have been dealing with since chapter 3 or 4. when we introduce the smooth contact, right? Every time there is the bar sitting at point A or at point B, as someone said last lecture, it works as kind of a roller, right? It can slide back and forth, right, in this direction, back and forth, but it cannot move in this direction. And therefore, that's why there is a normal force. But just to simplify it, they also says a contact, smooth contact, has always a normal force perpendicular to the surface. So we put NA and NB. Yes.
Can you take off your video?
Okay,
You're cutting
sure.
in and out pretty bad.
Okay. I hope it's better now. So the next thing we did, we wanted to add friction forces on it. We figured out the movement, which will happen at point A and point B, and we put a friction force perpendicular to normal force or tangent to the surface in opposite direction. Okay, so that's how we had the free body diagram last time. Any questions on the free body diagram? Okay, after this point, again, nothing new. You know the equations of equilibrium. We have our normal 3 equations of equilibrium, but we can add 2 more by stating this assumption and writing this sentence here. We say slipping happens at A and B at the same time. In other words, we are reaching that point in the diagram. This is the point we are writing this equation, FA equal mu and A and FB equal mu and B for. Okay, so then we have enough equations to solve all of our unknowns. All right. Questions about this? Okay. Let's go do another problem, another free body diagram. Okay. So let's see what's happening here. Beam AB. Is there a question? Okay. Okay, is it not good in the classroom, Colton?
It kind of comes and goes, but we can try it again. I just want to make sure it wasn't the other class 2.
Okay. Yeah, if it gets at a point that it's really hard to understand, let me know and I can repeat it. Okay, so we have a beam, says negligible mass and thickness, and it's supporting a 200 kilogram block sitting there. It is pinned at A and rests on top of the post, having a mass of 20 kilograms. So this post itself has a mass of 20 kilograms. Negligible thickness, okay. Find the force P needs to move the post. The coefficient of static friction at B and C are this and this. All right. Step 1 is to draw free body diagram of what? See, that's the important thing that you got to figure out, right? Because you got to know what are you drawing free body diagram of. Any idea? Should it be the whole thing? Should it be AB? Should it be the block? Should it be BC?
Jake said the post.
Okay, which one? There are 2 posts here. Oh, he probably
BC.
BC. Okay. BC. Okay, what else? So in problems like this, that there are 2 members, kind of sliding and moving in relation with each other. So let's look at it. BC is going to slide. So I'm going to have some friction here. I'm going to have some friction here, right? Because there are two posts, or a beam and a post, kind of sliding on top of each other. So because point B is common between the two, I have to have free body diagram of BC, but also I have to have free body diagram of AB. Okay. So we got to kind of like machines that when we dealt with them, or frames, take it apart and draw free body diagram of. Okay, so let's start with AB. That's easy. Step 1, outline of AB. Step 2, put active forces on there, which I only see this one, 209.81, and that's going to be newtons. Reactive forces. I have pin A. What kind of forces should I expect from pin at A? What kind of reactions does a pin generate?
Wouldn't there be a moment around it?
Okay, so someone said moment. What else?
Be X and Y reaction forces. No
X
moment.
and Y. It doesn't have any moment. Why does it not have a moment? A pin.
For you to rotate.
So remember, when we're drawing the forces, the reason there is an X and there is a Y, because this pin prevents the movement, right? So it stops beam AB from going left or right or up and down. And because it stops it, it generates forces. Or because it generates forces in that direction, it stops it. Okay, so in X, can it move? No. In Y, can it move? No. Can it rotate about point A? Yes. And remember, we only said these are going to generate reaction. So that's why it doesn't have a moment. Okay, so pin never has a moment on it as a reaction. All right. What about point B? What kind of reaction point B has for me?
A normal force pushing up.
It has a normal force pushing up. What else?
Wouldn't there be a moment since it's not supposed to rotate?
It's not a okay, here's the thing. So this is just sitting on the ground, right? And here's a pin. Okay. So let's call this A, let's call this B. A, we figured it out. Let's look at point B. If you have doubts, you have to draw this kind of table. So let's figure it out. Does it move in X direction? This way or this way?
Yes.
Yes. Does it move up or down?
No.
It doesn't. So I'm going to put no. Can this beam rotate about point B?
Yes.
Yes, it can. See, it's about not it's supposed to or it's not supposed to, whether it can or not. And when you do that, you only look at point B. It can rotate. There's nothing on point B stopping it from rotation, right? So the only thing that we got to take care of is no. It's no different if it was a roller. Same thing. It would result in the same free body diagram if this was a roller. It can move in X and Y. It cannot go up and down. It can rotate. Okay, so what else do I need at point B? What is this chapter dealing with?
A friction reaction.
Friction, okay. Friction is perpendicular to that normal force or tangent to the surface, right? This is the surface of contact right here. Friction, this is the surface. So friction is tangent. So friction is going this way. Let's put it in blue color. Okay. But is it going towards 1 or is it going towards 2? Let's call this one 1. Let's call this 2. Should the arrow point to 1 or point to 2?
2.
2.
2.
2. Okay. Anybody for 1?
Not yet.
heard
Everybody's saying 2.
Okay. What about other people that are not saying anything?
Technically, it doesn't matter because if it becomes a negative, it's just the opposite direction.
No. Okay, I'm really glad you said that because no, it's important. Okay, I'm glad you said that. For friction forces, it is important to figure out the direction of it. Okay, so don't put it any way you want. You're not going to get correct answer. You have to figure out which way they're pointing. Okay. So I'm really glad someone said that because I forgot to mention. We have to figure out if it's 1 or 2. Okay, you know what? I'm gonna leave it like this. I don't know which one. I'm really confused. I don't know what to do. I'm gonna leave it. I'm gonna move on to the post BC. Let's draw a free body diagram of that. Outline of BC, then put active forces, which it says how much, 20 kilograms, so 29.81 newtons. And then reactive forces. What is the reactive force? We have B already. It's going to be opposite of the other one, right? What is the reactive force at point C? Based on the X table or based on whatever you want to figure out. What is the reaction force at point C?
Isn't there a normal force?
Okay, which way, up or down?
Up.
It's up. If you want to go based on table, does it move in X direction? Yes. Does it move in Y? Nope. Can it rotate about point C? Yeah. So I'm just going to have just the normal force, okay? Oh, another active force I forgot. Force P, which we're trying to find, right? The goal is yes. What else?
Friction.
Friction at point A, B and at point C. So friction is going to be tangent to the surface, perpendicular to the normal forces. Tangent, tangent. Let's look at point C. Point C, should the friction point towards 1 or 2, 2?
2.
Okay, why? Why 2?
Because the active force is pulling it the opposite direction.
Because the movement, friction is opposite of movement, is to the right, right? My right, which is number 1. So the friction should be opposite of that. All right. So let's call this FC. And let's call this NC. What about point B? Is the friction pointing to 1 or 2?
It'd be towards 2.
2. It's because of the same reason. This whole beam is going to move to the right. So the friction is going to be going back. Okay. Now let's go back, look at the free body diagram. So now, what do you think? For free body diagram AB, this one, should the friction that we couldn't figure out, was too confusing, should it be to 1 or to 2?
It should be to 2 because the post is going to be moving the opposite direction.
Okay.
I would say to 1 just because of the free body diagram and the other part is going the other way, so you have to cancel them out if you want to put it back together.
Okay. So now we have 2. See, before it was just 2. Now it's 2 and 1. So what else? What else you guys think? I see more ones.
Aren't they the same force no matter which body you have? So when it pointed to.
It matters.
The class
this-
says 1.
Yeah, it's the same force, but it's on two different bodies. Okay. Okay, I see more 1. Someone said 2 because it would create a rotational moment. We never think about those stuff. We're just drawing a free body diagram. Free body diagram has 3 very simple steps. So if you want to start thinking about if it's creating a moment or it's not creating, that's going to get confusing. All you have to do is 3 steps, and we are in step 3, which is reactive forces. So from frames and machines, remember when you took something apart, and then when we said when you put it back together, we always said these should be opposite of each other, right? So someone already said it. Just 1 second, let me get. Okay, because my iPad is about to die, so I text my wife to get me my charger. So the friction should be opposite, because when I put these two together, they should cancel each other out. Okay.
Wait, so is it pointing towards 1 because relatively beam AB is moving the other direction?
Exactly. That was my next point. Exactly. Okay. So there are 2 reasons for it, and there are 2 ways you can figure it out. Okay. One is the way I did it. If you are in doubt, leave it. Go to the other free body diagram that is more obvious. And then on the first free body diagram, just put it opposite. Okay. That's the first reason, or first method. So first method is to draw the obvious one and then put opposite on the first one, right? You get what I'm saying. The second is friction is always against movement, right? So you have to find relative movement here. You have 2 posts sitting on top of each other. This one is moving to the right. It feels or seems like the other one is moving to the left. So they have relative motion. Okay, so based on that, you also see it makes sense. On this beam, the movement is to the left, and therefore it makes sense to have the force of friction going opposite direction. Okay, so I'll let you guys think about it for a second. Everyone kind of imagines these 2 beams, the green one, the BCs, will move to the right. It feels like beam blue is moving to the left. Does that make sense? So there are 2 ways that you can figure out friction if you guys get in a situation that is kind of confusing. Opposite of movement. Okay.
So is that
everyone...
because AX? Is that because AX has a force to the left?
No. It has nothing to do with force. This one, again, this was an unknown. I didn't know it, so I can just draw it this way. Okay. No. Again, I want to emphasize that when you're putting a reaction at a point, do not look at other parts of the free body diagram and what's happening elsewhere. Right now, we are putting reaction forces on here. That's where we only focus, all right? It's a kind of a narrow focus, a tunnel vision. We only look at this. We don't care about the other forces. No, the reason is not that. The reason is only movement against movement, okay? So let me see. I'm gonna leave this here unless there's a question about free body diagram. I'm gonna solve it, but I wanna draw another free body diagram now that we are on this topic. Okay, so let me draw another free body diagram, not this one. Let's do this one, okay? I'm only going to do free body diagram, and then I'm going to come back and solve it. Coefficient of friction are this much and this much between all surfaces of contact. Determine the smallest P required to start the 30 kilogram block moving. Okay. Let me quickly make sure I understand this graph here. This is Fs, this is Fk, and this is force P. It tells me find the smallest P required to start the 30 block moving. This whole thing is moving, right? On this axis, the smallest force that will cause moving is right here. So it's talking about this point. I just wanted to make sure I'm understanding the problem correct. So find this force P that will cause moving A if the cable AB is attached. Okay, let's just focus on A for now. Another question for you guys, which of these do I have to use? Mu sub S or mu sub K, and why?
Mu sub S, because that's the minimum amount that it'll take to get it to move.
So mu sub S, that's correct, because this is coefficient of static friction. And this problem is not dealing when the blocks are moving. It just wants to find out the smallest force to start. Other words, is impending motion. Just to, so it get it ready for movement, but it's not moving. So we don't deal with this one because this is for what? MK. What is K for?
When it starts to move.
It is
Or when
kinetic,
it's
right?
already moving.
It is when it's moving, and that's why it starts. It says MK because it means kinetic. So that's one thing. I think we have everything that we need. We understand the problem. So now the question. I'm only looking at part A for now. The figure as you see it. I gotta draw a free body diagram of what? The most important question that you have to ask yourself and answer. Of what?
The 30 kilogram block.
Okay, so block B. What else?
Then we needed a block A as well.
Block A as well, yeah. So there are only two blocks. We have to draw a free body diagram of each block. Why? Why can I just draw the whole thing together? Like this. What's wrong with that? Why do I have to have two different free body diagrams?
Because they have different forces.
Yes, but that's not the driving reason for me to do that.
You pull one, there's going to be friction upon the other.
The reason is this one is going to move this way, this one is going to move this way. There are forces in between these two created. Friction is created, right? The only way I can put those friction on a free body diagram is if I make it free, right? As long as they're attached to each other, I cannot put a bunch of forces here. This is wrong, right? I cannot do that. So therefore, I have to make both of these blocks free, draw outline of each of them. Now I can put forces on both surfaces. I think that's what the first person who answered said there are different forces. That's what they meant, right? There are forces between A and B that I need to have access to. So that's why I have to take it apart. Okay. So now let's start with A. Step one, done. Step two, active forces. What active forces do you see on block A?
The normal force.
Normal force is a reaction, kind of.
Oh, sorry, the weight then.
Weight, yes. So I see weight. I show it by WA or W1, whichever you want to show it. And that's how much? 29.81 newtons, okay? What else? There's one more active force on there.
Is it the pole to the right?
The tension, right? Great. Because if I apply P, it goes through that rope, it's trying to pull. So these are two active forces. Now we move on to reactive forces. What kind of reactive forces do I have?
Normal force pushing up from B.
Normal force pushing up from B. Let's call that N1. What else?
You have friction from B moving.
Friction from B moving. I'm going to draw it like this, tangent. Now we get to the big question here. Does it go to 1 or does it go to 2?
It'd go to 2 since it's trying to move to the right.
Okay. Okay. Yeah, I see another response from earlier that someone said A and B are going different directions. Yeah, absolutely. That's another reason you need two free body diagrams, because they're moving different directions. So anybody advocating for direction 1? Okay, so that is correct. The block A is going to move to the right. The friction needs to be opposite and going to number 2. Okay, but if you have doubt about this, you can leave it, do the more obvious one, because block B is more obvious. It's literally going to move to the left, and we can figure that out. But I think everyone is kind of having a good understanding here. F1. Let's move on to block B. Now it's going to be really easy, because the first thing I do, I'm going to put an opposite force here, opposite friction there. Okay. What else? I kind of jumped the line a little bit, cut the line. I put some of reaction forces there, but let's think about active forces. What about active forces do I need to put on there?
You have the weight going down and then the force P going to the left.
Okay, so force P going this way, tension going that way, and W, now it's a question. I have weight pushing down. Is my weight 50 kilogram or is my weight 30 kilogram?
30 because the other 20 is included in the natural force.
Okay, so Merrick says 30. What else? I think you meant normal force, the N1, right? What else? Anybody saying 50? Okay, so the correct answer is yes, 30. The reason is, one of the reasons is what Merrick said that weight of that 20 is already kind of, we are seeing the effect of it on N1. It's already included in there, right? But also the other reason is, and that's why I say it's super important to figure out what are you drawing free body diagram of. I'm drawing free body diagram of block B. And then I told you, it's a tunnel vision. You just got to look at block B, okay? On block B, all I know is it has a weight of 30 kilogram. I don't care what's on top of it. I don't care what's, below it, to the right of it, to the left of it. Is there a pulley? Is there a rope? I'm only focusing on block B, and all I know is there is a weight of 30 or mass of 30 kilogram. So W2, which is going to be on the one that I have on the right. One surface, I put the normal force. The other one, I still have to do it. What about the surface that's down here? What kind of forces goes there?
You'd have a normal force and a friction force.
A normal force and a friction force. That's always the case. Every surface that's a sliding is going to have a normal force and a friction force. Which way the friction should go, 1 or 2?
Just go to 1.
should go to the 1 because my movement or potential movement or my impending movement is going to be going to the left. Yeah, left. So it is going to the right. If I want to check my F1, yeah, that makes sense because now see F1 is also kind of fell right in place. And now it makes sense. Okay. So any questions about the direction of the moment? Oh, sorry, direction of friction forces I put on these. So a couple of points to remember. Every time you have surfaces that are sliding, slipping, rubbing, any of those in relation with each other, you always have a normal force which is perpendicular to the surface. Always. And you're going to have a friction that is tangent. I think tangent, it can be shown by this symbol. Tangent to the surface. In other words, it's perpendicular to that normal force, all right? And it's opposite of movement, opposite of, I don't want to say movement, impending movement. Okay, so that's the important thing to learn. And if you can understand this, you can draw any free body diagram with any friction forces on it. Okay, questions about free body diagram, about normal force, friction, any of that?
I had a question about normal force 2 on block B. So
Okay.
would that be the weight times gravity plus the normal force 1? Or would that just be weight?
Yeah, you're correct, because I mean I'm going to solve this, you know, but you're right, because for each of these now I can write my equations of equilibrium. And of course moment, but we're not going to use moment for this one because the dimensions of the block are not given. But you're right, if I write summation of forces in Y, N1 plus W2 should be equal to N2. You're correct. And then so I got to start from top there. Summation of forces in Y equals 0, so N1 equals W1. You know, you see that? So pretty much W1 plus W2 is N2, which makes sense. If it's a 50 kilogram on the ground is going to push 50 kilogram multiplied by 9.8 up. Well, I'm going to solve this, fully solve it next lecture. Okay. Any other questions? All right, so what I want to do is do a little quick quiz here. Okay. So here's a block with a weight of 20 kilogram. All I want you to do is draw the free body diagram of this block for me. Okay. That's it. I don't want to solve anything. Draw FBD of block. It's on an inclined surface of angle theta and is connected somewhere with a spring. All you have to do is draw a free body diagram of block. That's it. If you're in the classroom, draw it on a sheet of paper and Colton will snap a photo of it. Make sure to include your name. If you are online, there is a link, assignment, quiz 6 FBD. Just submit it to that link. Do not leave the call unless you submit it. All right? Do not leave the call before you submit it. On a sheet of paper, free body. And don't search it online. I totally made this up right before the class, so you will not find the solution anywhere. How many students we have in the class, Colton?
Only 5 today.
Okay, so yeah, so if you just snap a photo with your phone, that's good. They don't need to submit anything online.
Okay.
If you're done and you submit on Blackboard, you're good to go. I don't have anything else for this lecture, but that's the last thing we're gonna do. So do this, submit it on
Do we
Blackboard, and then leave.
Do we assume that the block is moving down for the direction of friction?
Yes, this spring is not, yeah. So this block eventually will move down. Yes, you're correct.
Oops.
Again, if you draw a free body diagram, submit it on Blackboard, and you're good to go. Otherwise, please do not leave the call. If you leave the call, I know that you don't have any problem and you've submitted everything.